Hello and welcome to the talk about achieving anonymity via weak lower-bound constraints for k-median and k-means. This is a joint work with Melanie Schmidt. For those of you who are not familiar with k-clustering, let me start with a few basic definitions. In the center-based k-clustering problem, we are given a finite set of points P, which we have to divide into clusters, a set of possible centers F, and a metric describing the distance between points. And what we want is to compute at most k centers from the set F and assign every point to a center such that in the end the data is clustered well. This assignment also gives us a partition of P into k clusters or subsets. Let me talk about common quality measures for k-clustering. There's the famous k-center objective, where we want to minimize the maximum radius of a cluster. The radius of a cluster is given by the maximum distance between one of its points and the center. There are also sum-based objectives where every point contributes to the cost of a clustering. For example, k-median, where we take the sum over the distances between points and their nearest centers, and k-means, where we take the sum over the squared distances between points and their nearest centers. And for k-means, the set P comes typically from the Euclidean space, and we are allowed to place the centers everywhere. We are now interested in clusters of some certain size, meaning that every center C gets a lower bound BC, and if we select C to be in our solution, then we also have to assign at least this much points to it. If the lower bound is the same for all centers, then this is a uniform lower bound problem. In the example on the left, we see the three clusters, so it may be that the lower bound is relatively large, such that the two clusters on the right just not have enough points assigned to it, so a feasible solution may be that we have to merge the two clusters and produce a larger cluster. So why are we interested in studying lower bounds? Suppose you're a company and you have to decide where to build facilities. Then it is sensible to assume that a facility is only profitable if it serves enough customers, meaning that with lower bounds we can determine profitable locations where to build later on the facilities. Or from another field, namely data representation, if we have to deal with sensitive data of people, then the process would look as follows. We would cluster the data and represent it throughout the k-centers which are published. But to guarantee the anonymity of each individual point, we want that the clusters are large enough. And for this, it is sufficient to establish uniform lower bounds. Therefore, we now only consider k-median and k-means with uniform lower bounds, but to mention this, our results also hold for non-uniform lower bounds. There are already several approximation algorithms for clustering with lower bounds. There's, for example, a true approximation for k-center with uniform lower bounds presented by Agarwal et al., and a 3 approximation for k-center with non-uniform lower bounds presented by Ahmadian and Swami. For facility location where the number of clusters is not bounded by k, but we pay a cost for opening a center, there Svitkina shows that there is a 558 approximation by a reduction to capacitated facility location, and this was later improved by Ahmadian and Swami to 82.6. A similar approach is also used by Lee to prove an 4000 approximation for facility location with non-uniform lower bounds. Especially for uniform lower bounds, the results can also be adapted to work for k-median, and we guess that this is also the case for the non-uniform lower bounds. However, we are not 100% sure here. So far, we don't know any approximation algorithms for k-means with lower bounds, especially the techniques which are applied for facility location, which easily convert to k-median, cannot be applied here as they use that the cost is a metric, which is not the case for k-means. But what we can show is that any facility location algorithm for lower bounds can be converted into an algorithm for k-median with lower bounds using the concept of nesting, which also directly shows that there is in fact an approximation algorithm for k-median with non-uniform lower bounds. And it also shows that restricting the number of centers is not that problematic when dealing with lower bounds. In contrast, for example, to capacities, where we know how to compute results for capacitated facility location, but don't really know how to restrict the number of centers. The concept of nesting was introduced by Linnetal 2010, and they used it as part of a framework to compute incremental and hierarchical clusterings. One can describe nesting as combining two clusterings with different properties into one clustering of bounded cost. So here, when we adapt this for lower bounds, we may have a solution which has lower bounds but has too many centers, and we may have a solution which has no lower bounds but at most k centers. The left can be computed with one of the algorithms for facility location with lower bounds, and the right can be computed with one of the algorithms for k-median. So we want to combine these solutions into one solution which has lower bounds and at most k centers, and we do this as follows. For every center from the solution with lower bounds, we compute the nearest center from the solution with k centers, and then we merge all clusters which have the same nearest center. This produces a solution which has at most k clusters, and it of course has lower bounds, such we merge clusters which individually always satisfy the lower bound. So we see that any algorithm for facility location with lower bounds also yields an algorithm for k-median with lower bounds. To say something about the cost of the combined clustering can be upper bounded for k-median by 2 times the cost of a lower bound solution and once the cost of the k-median solution. The nesting itself also works for k-means, but we are simply missing an algorithm which can compute a solution with lower bounds and arbitrary many centers on squared metrics. As I mentioned before, the algorithms for facility location do not work for squared metrics, and this is even the case for BCriteria algorithms. The algorithms for facility location with lower bounds typically start with a solution which may not have lower bounds satisfied at all centers, and it then closes centers where the lower bound is not satisfied and reassigns the points from it to other centers until we have a valid solution. So it may occur that, for example, this blue point here is assigned to the red center, and the red center does not have enough points assigned to it. So we would then close the center and reassign the blue point to another center, and this may happen several times. Now this does not pose a problem for metrics, as we always guarantee that we can upper bound each individual distance, here by 1, for example. So the whole cost which we have to pay to transport this blue point to the red final center is n. However, if we deal with squared metrics, the cost of reassigning this blue point is now n squared, and we cannot upper bound this by the individual steps. So since this approach seems not to work for k-means, and the algorithms for facility location with lower bounds also have very large approximation guarantees, we asked whether we can make this problem easier. Therefore, we introduced the concept of weak lower bounds, where we allow a point to be assigned to multiple distinct centers, meaning that now the assignment does not map into C, but every point is now assigned to a non-empty subset of centers. We want still that the lower bound is satisfied on every open center, and we adjust the cost as points can now be assigned to multiple centers. We also pay the shipping costs of these points to all their centers. Now this can produce solutions which are arbitrarily cheaper than solutions satisfying lower bounds, since it may be more valuable to assign points multiple times than closing centers. And this problem also occurs in this example below, where we have two locations with each b-1 points at a distance of delta. Then the optimal solution with weak lower bounds would just assign two of the points 2 times and induces a cost of 2 times delta or 2 times delta squared for k-means. But when we are considering lower bounds, there we see that we can only open one center, meaning that at least these b-1 points must be transported to the other one, incurring a cost of b-1 delta or b-1 delta squared. On the positive side, we can compute relatively easily a solution with weak lower bounds. For this, we have to assume that the number of possible centers f is finite. Especially for k-means, we can assume that the centers can only be drawn from P, and this increases the factor by 2. To compute weak lower bounds, we reduce this problem to k-median or k-means with center costs. This approach we borrow from Guha, Meyerson, and Munagala and Karga-Minkoff, who use a similar technique to compute a BCriteria solution for facility location with lower bounds. They increase the cost of opening a center by adding the distance to the b nearest points. So this increase in cost then pays for establishing the lower bounds. So we obtain the following result. If we are given a gamma approximation for k-median or k-means with center costs, we can compute a 2 gamma approximation to k-median or k-means with weak lower bounds in polynomial time. If we combine this now with the, for example, 4 approximation for k-median by Jane et al. And an O1 approximation for k-means by Jane Vazirani with center costs, we obtain in total that there is an 8 approximation for k-median with weak lower bounds and a constant factor approximation for k-means with lower bounds. The problem with weak lower bounds is that the number of centers which a point can be assigned to is unbounded. So in the worst case, a point can be assigned to all centers, and we want to prevent that by introducing 2 weak lower bounds. This is a variant of weak lower bounds where every point is allowed to be assigned to at most 2 centers. So now our main contribution is to show that we can compute solutions with 2 weak lower bounds in polynomial time. We do this by starting with a solution which has weak lower bounds and establishing that every point is assigned at most twice. This increases the cost of the solution by factor 2 for k-median and by factor 6 for k-means. So let me sketch the proof of this theorem. We start by defining C tilde A tilde to be the solution with weak lower bounds. We then fix an arbitrary processing order on the centers from C tilde. This will be essential to prevent multiple reassignments. We then consider the set PC of all points which are assigned to C by the assignment A tilde, and divide it into the 3 sets PC1, PC2 and PC3, where PC1 contains the points which are assigned exclusively to C, PC2 contains the points which are assigned to C and some other center, and PC3 contains the points which are assigned to C and to at least 2 other centers. So in the end, we want that the set PC3 is empty for all open centers, and to achieve this it may be necessary to close some of the centers from C. So if we close C, we have to care about points in PC1. Since they are exclusively assigned to C, we have to define where they are assigned to. So we distinguish PC1 by lonely and non-lonely points. We will not give an exact definition of these terms, but one can think of a non-lonely point as a point which has a center C' near to it, which is processed before C and which is contained in the original assignment A. So while processing C, the set PC3 is then emptied, and we at all times maintain that at least B points are assigned to every open center, and especially to the currently processed center C. We then process the center C as follows. As long as PC3 is non-empty, we do the following. We pick a center D which shares one of its points with C, meaning that there is a point which is connected to C and D and to at least one other center, and we pick this center D according to the processing order, meaning that among all centers which share point from PC3 with C, we pick the one center as D which is next processed by the algorithm. We distinguish two cases. If now PD1 contains at least one lonely point, which we call Y, then we delete the connection between C and X, and now the lower bound at C may be violated, and we replace this connection by connecting Y to C. So now Y is assigned to two centers and X is no more contained in PC3, so the cardinality of PC3 decreases by 1. In the other case, PD1 consists only of non-lonely points, and if we recall the definition of non-lonely, this means that every point there is paired to a center which is near to it. And then we can do the following. We close the center D, then we have to care about the points in PD1, but these points are simply assigned to their paired centers. So in the picture we have this non-lonely point Y, which is paired to the center C prime, and after closing D we reassign Y to C prime. In this case, the cardinality of PC3 may not decrease, but at least X is assigned now to 1 point less, so if this happens enough times, we achieve this way that this set PC3 is empty. In the end, we then obtain a solution which assigns every point at most twice. One can see this by the fact that while a center C is processed, the set PC3 is emptied, or it is not processed, then it was previously closed by the algorithm, such as D now in the picture. Also, we guarantee that the lower bound is satisfied at all open centers, and we never add connections to points which are assigned more than once. So here in the picture, in the first case, we assign Y to C, but this can only happen since Y is assigned only once. So in the end, we get a solution which has 2 weak lower bounds, and now it is left to bound the cost. The increase in the factor comes then mainly from the reassignment of Y to C. In the other case, where D is closed and Y is reassigned to its paired center, we guarantee that with the definition of non-loneliness, this connection was already present in the original solution, meaning that this does not increase the cost. However, if we assign Y to C, this is a new connection which we have to upper bound in the original cost. We can then upper bound the connection of Y to C by using the triangle inequality for k-medians or the relaxed triangle inequality for k-means by the distance of C to X, X to D, and D to Y, and we obtain the following inequality, namely that the distance, or the squared distance from C to Y, can be upper bounded by alpha times the distance of C to X plus alpha squared times the distance from X to D plus the distance of D to Y, where alpha is equal to Y for k-median and alpha is equal to 2 for k-means. This is a relaxed triangle inequality which holds for the squared metric. We then take the sum over all newly established connections, so connections which are depicted in this picture where a point y, which is previously assigned to only one center, is then assigned to the currently processed center C to maintain the lower bound at C. And as we mentioned, we can upper bound this by these three distances here with the respective factors. And now we can observe that these connections were already present in the original solution CA. This has something to do with the fact that these connections are already presented in the solution CA since the point is assigned at least 3 times, and we never add new connections to points which are assigned more than once. One can prove this fact also for the connection between Y and D. And if we then sum over all these newly established connections, we observe that every distance here on the right hand side in total pays at most with factor alpha squared plus alpha for the cost of these newly established connections. And with this we conclude that in total the cost of our solution is at most 2 times the cost of the original solution for k-median, or 6 times the cost of the original solution for k-means. Now we know how to compute solutions with 2 weak lower bounds. Let me now come back to lower bounds and talk about BCriteria solutions. A better delta BCriteria solution is at first a delta approximation in cost to an optimal k-median k-mean solution with lower bounds, and second, it assigns at least beta times b points to every selected center, meaning that it is allowed to violate the lower bound by some certain factor, namely here by 1 minus beta. As I mentioned before, there are BCriteria algorithms for facility location and k-median regarding lower bounds, and for k-means this is still unknown since we have this unbounded number of reassignment steps which does not behave well when dealing with squared metrics. But now we can use the solution for 2 weak lower bounds to compute a BCriteria solution for k-means with lower bounds. This leads our final result, namely given a gamma approximate solution CA to k-means with 2 weak lower bounds and a fixed beta which is at least 1/2 and at most 1, we can compute a BCriteria solution to k-means which assigns every center at least beta times b points and is a gamma times 4 beta over 1 minus beta approximation to a k-means solution with lower bounds. So that were our main results regarding clustering with lower bounds. I hope you enjoyed the talk and thank you for your attention.